Today's lecture, number 32, is on chapter 10.4 and 10.11 on phase changes and phase change diagrams. So we introduced the idea of intermolecular forces as it is used to maintain different phases of matter, whether we're talking about solids, liquids, or gases. And so we've implied that there's the ability to change phases, but let's implicitly go over that material. So a phase change is defined as a change in the physical form, but not the chemical identity of the substance. And so we know that fusion or melting is going from a solid to a liquid, vaporization is going from liquid to a gas, sublimation is going straight from a solid to a gas, whereas freezing is going from liquid to solid, condensation is going from a gas to a liquid, and deposition is going straight from a gas to a solid. Okay, so you can see we can go between solid and gas either directly through sublimation and deposition, or we can go via the liquid intermediate. Okay, and don't worry about this enthalpy or entropy business here. That'll come in general chemistry too. Okay, so just know the actual identity for, or the names for each of these transformations. So if we can take a look at what's called a heating curve, which indicates the amount of heat that has to be put in on the x-axis and the temperature on the y-axis. Okay, and so this talks about, so we know if we want to go from, so if you consider the changes of phase for water, we know that we can have an ice cube. And if we put in a small amount of heat, we can melt that ice cube all the way from the solid ice cube into liquid. And then if we keep adding heat, we can then cause that liquid to start to boil. And then eventually all of that liquid will be converted from the liquid water state into the vapor water state after we add a ton of heat to it. Okay, so this heating curve for water talks about the amount of heat that you have to add to change the temperature of a solution in order to change the phase. So we can see here so for water, we know that the freezing point for water is 0 degrees Celsius, and the boiling point for water is 100 degrees Celsius. So we see when we add heat to a block of ice, we can steadily increase the temperature, but then the temperature maintains the same value during the entire amount of heat added to melt that ice into liquid water. Okay, so if you have a solution of ice and water together, that ice and water should be held at 0 degrees Celsius. And then as we continue to add heat, we can see a linear increase in the temperature of our water until we reach 100 degrees Celsius, where that water begins to boil. And then, so as we're boiling off that water, we need to add an absolute ton of heat in order to convert all of that liquid water into water vapor. And so that boiling water, even though we're adding more and more heat, is going to maintain at that 100-degree boiling point temperature. And so these two different flat portions of our heating curve, we can give specific names. So this first one is called the heat of fusion, which is the amount of energy required to overcome the enough intermolecular forces to convert a solid to a liquid. All right, so for melting. And the second one here is the heat of vaporization, which is the amount of energy necessary to convert a liquid into gas. And so we can see here the amount of energy that it takes to melt is much smaller than the amount of energy that it is to boil. And this makes a lot of sense, really, if we think about the intermolecular forces that hold together solids and liquids versus gas. So to go from a solid to a liquid, you just need to weaken the intermolecular forces that's holding a material together. Whereas if you're going from a liquid to a gas, you go from having intermolecular forces that hold together individual molecules for a liquid into a gas where there are no intermolecular forces that are interacting between different molecules. Okay, so you have to totally break add enough energy to totally break all of the intermolecular forces in order for vaporization to occur. So it requires much, much more energy or much more heat in order to totally break that interaction. So we can indicate the dependence on the individual phases of matter for a specific material by looking at a phase diagram. So phase diagrams show the temperature of a material on the x-axis, and the y-axis is the pressure that that material is being held in. And we can see that we have a few different lines here that are indicated here in black that separate our solid phase, our liquid phase, and our gas phase. And so for any specific combination of temperature and pressure, we can look up and see where on this phase diagram that we're actually located to indicate whether we actually have a solid or a liquid or a gas. And so each specific material has its own designated phase diagram. So this one, for example, is from water. For water. So we can see that we have a couple different junctions here. So we have a line here that tells us the difference or the conditions where we can convert straight from a solid to a gas through sublimation or deposition. And we have our boundary here, which we can go through between solid and liquid, so our melting or our freezing. And then we have our junction here going between liquid and gas, so through our vaporization or condensation. And so we have a couple different key aspects or key elements to this phase diagram that we need to define. So we're going to sort of switch back and forth a little bit between the next two slides. So when we're talking about phase diagram, if you're talking about normal pressure condition, that talks about the pressure at 1 atmosphere. So we can see the 1 atmosphere pressure that's listed on this phase diagram, that's considered the normal pressure. So that's because that's the typical atmospheric pressure that we're in without any compression or anything on Earth. 2, the critical point is the combination of temperature and pressure, beyond which a gas cannot be liquefied. Okay, so the critical point, you can notice that this line here that goes the junction between liquid and gas ends at a certain point. And so this end of the line is called the critical point. And so that's where you're forming one of our other elements here, the supercritical fluid, which is a state of matter beyond the critical point that's neither a liquid or a gas. So when you pass the critical point, you reach this supercritical fluid where you are sort of in a in-between state between liquid and gas states. Okay, the next is the critical temperature and the critical pressure. That's the temperature and pressure that correspond to that individual critical point. Okay, so the temperature and the pressure. And lastly, the triple point is the point at which all three phases coexist in equilibrium. So we can see that triple point is where these three different lines meet each other. It's a specific temperature and pressure. So right here, this is the visualization of the triple point of water. So when you hold at the perfect temperature and pressure combination, you can see that we have solid water as frozen crystals, we have liquid water, and then we also have vapor water as a boiling solution. So if you actually have the chance to work through this experiment, the triple point is a really interesting sort of phenomenon to observe. So if we take a look here, we can see that as we said previously, that each individual material has a specific phase diagram. So you can observe that the water phase diagram that we looked at before is different than the carbon dioxide phase diagram. But all of our individual elements are still there. We have our critical point, we have our triple point, and then we have our normal conditions. And so for carbon dioxide, you can see here that we go straight from solid to gas at our normal conditions. So if you have dry ice, it goes straight from the solid to the gas phase. It goes through sublimation at our normal temperature. Okay, so at any specific temperature and pressure, you can tell us which material, what's the phase of matter of an individual material? Is it a solid, liquid, or a gas? So one key element that I wanted to point out about the water phase diagram is a very interesting fact. So you may have noticed just through living life that you can actually cut through a block of ice using pressure. Okay, so think about if you put an ice cube in your mouth and you just squeeze down with your molars and you bite down on that ice, you can actually cut through that ice with your teeth by adding pressure to that ice. You are not putting a substantial amount of thermal energy or heat into that ice in order to cause it to melt that fast. You're actually increasing the pressure. So why does that actually occur? So if we take a look at the phase diagram, we can actually explain it. We can see that the junction here, the line going between solid and liquid, has a slope that goes backwards. Okay, compared to if we jumped back to carbon dioxide, we can see the slope between the solid and liquid goes to the right, forward. Whereas for water, the slope goes to the left. So what that means is that if we're at atmospheric pressure here, we can go between solid and liquid at a certain temperature. But if we add additional pressure, holding at that same temperature, we can see that we can change now from the solid to the liquid state. So what that has the effect of doing is melting ice by pressure instead of temperature. So if you have a big block of ice and you put a wire with a few weights attached to it, these weights will eventually cut through the entire block of ice that's held at 0 degrees Celsius. Even though it's not increasing the temperature at all, that pressure can actually cause the melting to occur. So that's a sort of an interesting aspect of using our phase diagram that we can tell at any pressure and temperature condition what the exact state of matter will be. All right, that's it for the day. Thank you.